an iteration formula, the starting value. The iteration converges. The same iteration formula, a different starting value. This time the iteration is blowing up. We say it's diverging. So if you iterate with this formula and the starting value 0.6, then the sequence you get converges. And this figure, that's about 0.5354, remember, that's an approximate solution to the equation you get by ignoring the n plus 1 and the n. Remember, that's what formula iteration is all about. You've got an equation to solve. First thing you do is rearrange it into x equals something. You can then make that into an iteration formula by putting in an n plus 1 and n. But how can you check that the rearrangement is a good one? In other words, does it give an iteration formula that will lead to a convergent sequence for some suitable starting value? Well, in this case, starting with 0.6 does give a convergent sequence. But starting with 1, we get something which doesn't converge. And what about, let's say, minus 0.5? What would that do? You see, what we're after is some sort of test for an iteration formula. We've got an iteration formula. Can we find conditions which will enable us to predict with certainty that we'll get an iteration which will give a convergent sequence for a suitable starting value? Well, just looking at sequences of numbers isn't very informative. We can get a clearer picture of what's happening in the iteration process if we look at it graphically. We have xn plus 1 equal to a function of xn. We plot the graph of the function and then the line y equals x. Now, pick a starting value x1. To do iteration graphically, from x1 we go vertically to the curve, and now horizontally to y equals x. And vertically down again, that gives us x2. Repeat the procedure. Vertically to the curve, horizontally to y equals x. That gives x3, and then x4, and so on. From this starting value, we've got a staircase that converges on the intersection. And the intersection corresponds to a solution of the equation x equals f of x. That's a picture for converging iteration. But iteration needn't always converge. With a different starting value, we again produce a staircase, but this time it's going away from the intersection. This is the diverging case. Now we're interested in convergent sequences. And graphically, what happens is the iteration produces a sequence of points on the curve. They get closer and closer to a point of intersection. Now, how do these points relate to the numbers produced by the iteration? Well, we start with the value x1. We move vertically to a point on the curve with x-coordinate x1. Now, its y-coordinate must be f of x1 because it lies on the graph of f. And f of x1, of course, is x2. So this point has coordinates x1, x2. Let's look at a close-up of the way the iteration staircases into the solution. From x1, x2, we move horizontally to get a point on the line y equals x. Its y-coordinate is the same as this y-coordinate. It's x2. And because it's on the line y equals x, its x-coordinate must be the same as its y-coordinate. It must be x2 also. Now, vertically. And we move back to the curve again. And that gives a point with x-coordinate x2. So we've transferred the x2 from being a y-coordinate to being an x-coordinate. And if x2 is the x-coordinate of this point, then its y-coordinate must be f of x2, because it lies on the graph, and that's x3. Repeat the process. We get x3, x3 on the line y equals x, and then x3, x4 on the curve, and so on. And we produce a sequence of points on the curve converging on this point of intersection, alpha, alpha, where alpha is a solution to our equation. This iteration converges because these distances get smaller and smaller. That is, x2 is closer to alpha than x1, which we can express like this. Remember, modulus measures distance. Similarly, the next term, x3, is closer to alpha than x2, and we express that like this. And if each term is closer to alpha than the previous term, well, we can write that like this. Well, that looks like a reasonable idea for a condition for iteration to converge. But the picture gives us a more informative way of expressing this. We can rewrite this expression like this. And now this expression is really quite useful, because you see that thing inside the modulus signs there is the slope of the chord joining the point xn plus 1 to the point alpha alpha. So this condition now really means that each chord has the slope whose modulus must be less than 1. And if we look just at the first point, x1, x2, that's what we get when n equals 1. The slope of that chord must be less than 1 in modulus. So if we want our iteration to converge, we should make sure that our formula and starting value lead to points whose chords to alpha alpha have slopes with modulus less than 1.
So now we've got a good graphical condition for convergence. But there's just one snag. We don't know where alpha is exactly. That's the number that we want to find. And also, though we know x1, we can't predict in advance where x2, x3 and so on might be. What we need is to find some interval along the x-axis which contains alpha, so that when we choose any other point in that interval and we go up to the curve, then the chord joining that point to alpha alpha has slope with modulus less than 1. So let's look at an arbitrary point in the interval we want. Now, this is the chord whose slope we're interested in. Now, working with chords is nigh on impossible, especially when you don't know either of its endpoints. But it's not the chord itself which is important, only its slope. And there are lots of lines which have that same slope. In particular, there's this tangent. And the tangent touches the curve at a point between the endpoints of the chord. Now, tangent slopes are something that we know how to calculate. So I reckon that instead of my difficult condition on chord slopes, it will be just as good to use a tangent slope condition instead. And this tangent condition will tell me what I want to know about the chords. Now, suppose I have an interval containing alpha such that the modulus of the tangent slopes is less than 1 for every point in this interval. If we take any point in this interval, remember, we're looking for chords joining this point to alpha alpha. Now, this chord has a parallel tangent which is attached to the curve somewhere in between. And that point of attachment also lies within the original interval. So the slope of that tangent has modulus less than 1. Therefore, the slope of the parallel chord we want to know about also has modulus less than 1. So modulus of tangent slopes less than 1 implies modulus of chord slopes less than 1. So we can replace the impossible chord slope condition by an easier tangent slope condition.
Let's see how we could apply this tangent condition in practice. For this curve, there are 2 points where the tangent slope is actually equal to 1. On the left-hand end, the tangents have positive slope, but it's greater than 1. As we go along, the slope gets less. At this point, we actually have a horizontal tangent, whose slope, of course, is 0. Then the slope becomes negative. It never gets down as far as -1. It changes its mind and comes back to being horizontal here. And then it's 1, and then out here it becomes positive and greater than 1 again. So in this open interval, all the tangents at all the points on the curve above the interval have slopes that lie between -1 and +1. So the graph gives us a rough idea of the interval we want. But tangent slopes are something we can calculate precisely. This is the graph of the function f. Then the slope of a tangent at any point is given by the derived function, f prime. So our geometric condition can be replaced by an algebraic condition involving the derived function. This condition, that the modulus of the derived function should be less than 1, is a key test. When you've got an iteration formula, test to see where the modulus of f prime is less than 1. If your derived function has modulus greater than 1 for all x, then don't bother trying to iterate. You don't have a hope of convergence. Or if you have an interval where this inequality is satisfied, but alpha isn't in that interval, once again, you can't get a sequence converging to alpha. Look for another rearrangement. Now, in our example, we know we get a convergent sequence when x1 is equal to 0.6. So let's see how this condition could have predicted this convergence. Firstly, we look at the function from the right-hand side of the iteration formula. Its derived function is 3x squared minus 11 over 16. Now we want to find an interval in which the modulus of this derived function is less than 1.
We've got to solve this inequality. The modulus of 3x squared minus 11 over 16 is less than 1. And another way of saying the same thing is that 3x squared minus 11 over 16 lies between -1 and +1. So basically we've two inequalities. There's 3x squared minus 11 over 16 is less than 1, and 3x squared minus 11 over 16 is greater than -1. And we've got to find the values of x which satisfy both inequalities at the same time. Well, we'll start with the left-hand inequality. This means that 1 minus the quantity 3x squared minus 11 over 16 is greater than 0. And that simplifies. And now factorize. So we're looking for values of x where this expression is positive. As -3 is negative, we want the rest of the expression to be negative as well. And the way to do that is to look at the two factors separately. We'll draw a sign diagram for x minus 3/4. Starting with negative numbers, this factor is negative up to x equals 3/4. For x greater than 3/4, the expression is positive. For the other factor, x plus 3/4, it's negative up to -3/4, and it's positive afterwards. Forming the product, we only get negative values between -3/4 and 3/4. So the values of x satisfying this inequality lie in this interval. Well, that's the solution to this inequality. But we want values of x which satisfy this inequality as well. Now, this inequality means that this minus this is positive. So 3x squared plus 5/16 must be positive. Well, look at x squared. That's always positive or 0, and so is 3x squared. And we add on 5/16. So this whole expression is always positive for every value of x. So this inequality is always true. And this one's true between -3/4 and +3/4. So the interval we want, where the original inequality holds, is the intersection of these two. And that's just this.
What Bob did was to take the derived function of the iteration function and find those values of x for which the derived function has modulus less than 1. And he found that when x lies between -3/4 and 3/4, then the modulus of the derived function is indeed less than 1. So, if you take any point in this interval, the tangent at the corresponding point on the curve has slope of modulus less than 1. Now, there's another important fact about this interval for our purposes. We know it contains a solution to our equation. Well, that looks clear enough from the diagram. But we could check this by calculating the value of the function at each endpoint. That would tell us that the curve lies below the line y equals x at this end, but it lies above the line at this end. And so we would know that the curve must cross the line somewhere in between. Now, this all means that the interval contains a solution of the equation. And if we start an iteration with a point in this interval, then the next term must be closer to the solution. We've seen 2 iterations already. Starting from point 6, we got something which converged. And of course, point 6 is in this interval. Starting from 1, which is outside the interval, we got something which diverged. Now, what about minus a half? Well, that's in the interval. Now, does that mean that the iteration will converge? What do you think?
Well, that's a bit embarrassing. It's not converged. Well, why not? We started in the interval, so we should have got closer to alpha. But x2 is outside the interval. And x3 is even further away. And we get a staircase away from the solution. Well, how did we manage to jump outside the interval? Starting in this interval guarantees that x2 is closer to alpha than x1. And so it is. Alpha is here, and x2 is closer than x1. The problem is that x1 starts so far away from alpha that when it jumps over, it gets outside the interval. There's not enough room on this side of alpha to be sure of getting into the interval. So x3 needn't be closer to alpha than x2. In fact, it moves further away, and we get a diverging sequence. So our condition mod of f prime of x is less than 1 is an important condition, but on its own it won't guarantee convergence. If we start too far away from alpha, we could jump over alpha and end up outside the interval. So we need a second condition. We must start our iteration near enough to alpha to make sure we can't jump over alpha and end up outside the interval. So how can we be sure that we're starting near enough to alpha? The trouble is that we don't know the value of alpha. What we do know is that alpha lies in this big interval. But this interval's too big. We don't need a smaller interval containing alpha. Well, how about that one? We can check that it contains alpha by showing that the curve is above the line at this end and below at the other end. If we start with x1 in this interval, are we near enough to alpha? Well, what's the furthest that x1 could be from alpha? It's got to be the length of this interval. Alpha might be at this end, and we might start at the other. We must make sure that if we jump over alpha, we don't go outside the big interval. And that'll be okay if we have an equal amount of space on the other side of alpha. On the other hand, alpha might be at this end, and we might start at the other. So we need the same amount of room on the other side. So we need a small interval containing alpha, which has an equal amount of elbow room on either side within the big interval. If we start inside an interval like that, we're bound to get convergence.
So now we have 2 conditions to check for a guarantee of convergence. The first condition is essentially a check on the function itself. The second condition is a check on the starting value. Between them, These two conditions will guarantee us a convergent sequence. So let's finish by going back to our problem from the start of the program. Can I pick a starting value that I can guarantee convergence for? Now, I know that the first condition is satisfied between -3/4 and 3/4. And from the graph, I can see also that I have a solution somewhere around here, between about 0.5 and 0.6. So let's test to see if any starting value in this interval will give me a convergent sequence. Do I have enough elbow room on either side? Well, certainly there's enough elbow room on this side, and the distance from here to here is 0.15, which is longer than the length of that interval. So there's enough elbow room on that side as well. So that confirms what we saw at the beginning of the program, when we used 0.6 as a starting value, and we got a convergent sequence. Now here's a question for you, and one that you should be able to answer now. What will happen if I start iteration with a starting value of 0.5?